All right, well, it's a couple minutes after 4:30. And so I guess we'll get started. Welcome again to Energy 101. This is week 2. So welcome back if you were here last time, and welcome if you didn't join us last week, but you were here this week. We're happy to have you. I'm Megan. I am the Program Manager for Advanced Learning Initiatives at the Irving Institute for Energy and Society. And before we get started, I just want to give my colleagues from the Irving Institute a chance to introduce themselves for folks who weren't here last week. So Elizabeth, let's start with you.
Last week. I'm Elizabeth Wilson. I'm the director of the Irving Institute for Energy and Society, and I am a professor in environmental studies. And I'll pass it to Stephanie.
Hi, I'm Stephanie Garcia. I'm the program coordinator here at the Irving Institute, and I'm going to pass it to Amanda.
Hi folks, I'm Amanda. I am the academic director at the Irving Institute, and I'm going to pass it over to Angus.
Hi, my name is Angus McReynolds. I am the undergraduate education and internship coordinator for the Institute, and I'll pass it over to Stephen.
Hi, I'm Stephen Doig. I work on research topics at the Institute as well as special projects. I think
great. Thank you. Oh. All right, welcome again to everyone. Thanks so much for joining us, and thank you to those of you who submitted your questions in advance. So we're looking forward to having a great discussion. Today, our topics are everyone's favorite flowcharts, the Sankey energy diagrams, and the complicated social and technical nature of our energy systems, and also our evolving fuel mix. But before we get started, just a couple of housekeeping items. So please try to remember that while you're not speaking, to keep your mic off. And we're going to be using the chat and hand raising functions to ask questions. So if you're having any trouble with that, let us know. And we're going to start off this week having you go into a breakout and chat with each other. And so we're going to discuss the same topic that we did last week, but focused on this week's topic. What was something that you found surprising or interesting, or something that was really thought-provoking about the 3 topics that we explored in the videos this week? So Stephanie's going to go ahead and put you into some breakout groups, and feel free to chat, or you can even talk about maybe a question that you were left with that you submitted, but something that just really kind of struck you about the videos this week. Looks like everyone is back. Okay, I hope you all had a good discussion in there, and maybe you got some ideas for some more questions you'd like to ask. But let's get started with our Q&A for today. Thank you again to those of you who submitted questions in advance. And if you have any questions that you'd like to ask that you haven't had a chance to submit, then feel free to use the hand raising function or enter your questions in the chat, and we'll try to get to as many as we can. But so I'm going to start off with a question about the Sankey diagrams. And we have a question that was asked by a couple of you at least about other versions of the Sankey diagrams. So, so can someone tell us a little bit more about whether the Lawrence Livermore National Lab is going to be releasing more versions of the Sankey diagram, international versions, or what else is available or possibly coming up soon?
So I can jump in on that if you like. I know in the video they say that the international Sankey diagrams will be coming soon, and unfortunately I think they're still coming soon because they're not up yet, right? So if for most countries you can find a 2011 version of the Sankey flowchart for energy. If you look at the if you sort of draw down under commodities and select energy, then you can go to where you can see all the different flowcharts. There are some countries where you can find a 2017 Sankey. We were just playing around with it just now in the breakouts. And so but it varies widely, right? And they have also fairly recently updated many, if not all, of the state Sankey diagrams. So you can go and see your own state, and for many of those, you've got a 2019 Sankey diagram, which is pretty up to date because the US one is really only is from 2020. So the most recent one is from 2020 at this point. They usually come out in about April with the new national ones. So yeah, thank you, Elizabeth, for putting the URL in the chat for where to go. for all the Sankey diagrams almost all the Sankey diagrams you could ever want.
Right, great. Thank you so much, Amanda. Okay, so let's move on to our next question. So there's a lot of information in the Sankey diagram. Is there any aspect of the Sankey diagram that includes energy that's used by the agricultural industry?
Stephen, you want to tackle that one?
Sure. I mean, I don't know specifically if there's been a Sankey diagram for the agricultural industry. It's sort of embedded in the diagram as it is right now in different ways, in that agriculture uses transportation. It may have process facilities, which would be industrial. So on the left side, where you sort of see residential, commercial, industrial, that stuff, it gets buried in there. And if you want to know more about it, typically what you have to do is go to the EIA or something like that and ask, just query what's the agricultural uses of energy, and then you can get a breakdown. So for example, in milk, a lot of energy goes into drying milk, some of it into processing and other forms, but that's where you would find that information as far as I know typically.
I was just reading on the website link that I gave, and they said they'd done one of organizations before, like the Air Force, but I couldn't find it when I started to look for it. So, I mean, you can imagine this for Dartmouth College. You can imagine this for different processes of thinking about that, but it's
And I realize I sort of breezed over the fact that you can find Sankeys for other countries is a true statement. But maybe if we took a quick look at one, for example, here's one for Russia. Right, so this is a 2017 flowchart for Russia. We can see how different it is from the US diagram, right, where, for example, here under petroleum, we've got this huge degree of internal production and then this huge degree of exports on the petroleum side. Same for natural gas, because they're one of the biggest producers of oil and natural gas on the planet. And you'll see that, but you'll see that there are some things that are obviously also in common, right? The 2/3 of the energy that's consumed is lost as rejected energy, and about 1/3 or less, right, is actually directed towards energy services, right? So just to give you a sense for what you might be able to see there. I don't know if there's anything else that, Elizabeth or Stephen, you might notice from this one, or if you want to pull up a different country, either now or later on in the show, but they are there.
Well, one thing I would say, Amanda, I think one of the questions that came in, is there anything that's missing from the Sankey diagram? And despite my clip earlier about it, everything is in the Sankey diagram. In fact, there's one glaring omission in the Sankey diagram, which is energy efficiency. So that rejected heat over on the upper right side, which is 2/3 of all the energy essentially consumed in the world, can be reduced through energy efficiency. And so this middle section here of electricity, residential, commercial, industrial, all that, imagine if all of that was twice as efficient. Then the right-hand side rejected energy box would go down by half, and actually all the inputs on the left-hand side would go down as well. And so the Sankey diagram does not recognize the equivalency of a kilowatt hour saved as being the same as a kilowatt hour produced.
And I want to add one other thing is it doesn't add in the political or social realities either. I mean, how the energy distributed, what the energy burden is, how it affects different populations, what the externalities are. There's some now that do CO2, but there's not ones that are doing the criteria air pollutants or understanding who's affected. So this is a map, but it's an incomplete map that is kind of, we were joking earlier, it was kind of the airbrushed version of our energy system. And while it's useful to help us understand these different points in decision making, appreciating how these systems work in practice is something that we hope to get you a little more interested into.
Yeah, that is a very good segue to the next question that I was going to ask here, which sort of ties our first and second videos together. And it's, are any institution or organizations developing a Sankey diagram that includes the complex social, environmental, economic, cultural, and technical interactions of the energy system? So is there anyone out there who's trying to actually visualize that? That sounds like a challenge.
It is a challenge. Actually, Elizabeth and I had a conversation with one of our colleagues at Arizona State University about this. It's a problem. It's a problem for teaching. It's a problem that many of us are visual learners, right? And so developing a good representation of a complex social and technical system, I think it can be a big obstacle. And so, we've trying to have discussions to see, could we pull together some artists, right? Some data visualization people, some modelers, right? To try to figure out if there is a set of elegant ways to convey the social and technical complexity of these systems. So I'm not aware of it. Maybe Elizabeth, maybe you are, but I think it's a real bona fide research and communication challenge.
Yeah, I mean, Amanda's right. Our conversation with Clark Miller at ASU really highlighted how it makes it hard to talk about where these decisions are happening in social areas. And it's hard to show the kind of nodes of decision making, how you actually push here and pull there to make systems change. I have a lot of colleagues who, have these AI optimized energy futures that don't really involve people. Maybe you're an agent-based model that's working here and there, but a lot of what they're trying to do is optimal, but currently illegal. And so, if they want that optimal future to come, you actually need to change the regulations and the policy and, these different IEEE interconnection standards. There's a lot of like system stuff that needs to evolve to allow our system to evolve. And I think that question of how do we create these future energy systems, given our institutions, given our regulation, and these new technological capabilities is really where the energy and society story gets pretty juicy.
All right, thank you. All right, so we're going to come back to the socio-technical side, and I'm going to move on to a couple of questions that a lot of you were really interested in. But first, before I ask those questions, there's one in here that I want to make sure we cover because it's about definitions, and I think that's important. And I think someone asked, Stephen, if you could define what you mean by energy density, which is a term that I think came up a couple of times. So if you could just clarify what that means for folks, that would be great.
Yeah, sure. I mean, energy density is the amount of energy available per unit something. So the amount of energy available in a pound of something, the amount of energy available in a volume of something. And so, for example, gasoline and diesel fuel are very dense. They have a lot of energy per gallon, a phenomenal amount compared to, say, batteries. And so that's a volume way to look at it. The other one is energy per unit weight. And again, gasoline and diesel are very, very energy dense per pound compared to batteries. Many, many times more, like a factor of 10 more energy in a pound of fuel compared to a pound of battery storage. And these are really important factors because if volume and weight matter to you, so weight matters, say, in an electric vehicle, you don't want all your weight to be in the batteries, nor do you want all the volume to be in the batteries because you could drive a electric vehicle then that had no room for any passengers and couldn't possibly carry any additional weight, and that would not be a good solution. And so the real challenge has been, say, for electric vehicles to say, how do we get the volume density up, so the amount of energy we get per unit of area of volume of the car we're using, and how do we get the weight down, so the energy density per unit weight down. And that's been the real revolution in the last 10 years is the batteries are much lighter, lithium ion is much lighter than lead acid. And the energy per cubic foot is much higher. And that then allows you to switch from gasoline to electricity in a way that does not harm the attributes of the car that people really care about, which is driving distance and ability to carry passengers and other things like bicycles and groceries and things like that.
Great, thank you.
Megan, there's another example that's sort of close to home of that. When Dartmouth was considering using wood woody fuel for its electric and heat generation facility. I mean, a very legitimate concern there was the fact that wood is much less energy dense than oil, and therefore the number of deliveries that they would require and the space they would require to store the fuel would be really overwhelming for downtown Hanover, right, where the cogen facility is located. And so it has a material impact on device design, as Stephen said, but also on facility generation fuel choices.
All right, thank you. All right, so our next question is associated with fuels. And one of the things that we mentioned the Sankey diagrams don't show, right, are the risks that are associated with our energy production and our energy use. And so this question is asking, what are the environmental costs associated with extracting materials like lithium to create more efficient batteries?
Would you like me to take that one, Megan?
Sure, anyone can jump in.
Yeah, so I was actually just today working with the New Hampshire Electric Co-op, a local utility that serves part of the New Hampshire area, and myself in particular in line. And we were talking about vehicle electrification and the benefits that could bring to reducing the carbon footprint of their customers. And we're looking at some data that shows you that in the case of electric vehicles, the carbon that needs to be the carbon that is rejected into the atmosphere to produce an electric vehicle is higher than that for a combustion engine vehicle. And in fact, it's significantly higher if they're very high greenhouse gas emissions to get some of the really important metals. And so right now, people are working very hard to say, how do we reduce the carbon footprint, the climate impact of getting these rare earth metals, lithium for batteries, and really addressing that in a couple of ways. One, we can probably use more economical, or not economical, but efficient extraction techniques. We can also optimize the use of those materials. And then people are looking very hard at alternatives. So lithium is not the only option out there. Cobalt's not the only option out there. And so where chemists and material scientists are really working hard right now is to say, what can we do to substitute the higher impact metals that we extract from the earth that are being used to help us transition to a more efficient transportation or electrical system, or building heating systems over time. And the other thing I would just mention is that while the energy and the carbon footprint required to build an electric vehicle and put in the batteries is higher than a combustion engine vehicle, after probably 3 years, 4 years, based on the data I saw today, the net impact is lower for the electric vehicle because it's not consuming fuel and creating carbon dioxide from the fuel that it burns, which is roughly 70% of the total carbon impact in the lifetime of a conventional vehicle.
Thank you. And there was a question in the chat here, a follow-up question that Stephen.
I had written back to, and I keep sending it directly to her, not to everybody. Sorry about that, guys, to memory, where it just was like an explainer on lithium and where it's coming from. I do want to highlight for folks that in the spring term, we have these different themes. And our theme in the spring term is energy, minerals, and materials, because these are important geopolitical issues. These are important issues when you're thinking about the life cycle of different technologies. So if any of you have particular topics that you think are interesting there, please tell us what you care about, and we'll try and get as much program. We're doing this in conjunction with the Thayer School. And so they'll have some of the more technical talks, and we'll try and bring in some of these different socio-technical aspects of thinking about commodities like lithium and cobalt and others, and the water issue as well. So you're not only thinking about the lithium and the energy use, but also the water use, because a lot of in Chile or in Australia are places where it's pretty water poor.
Hey, thank you. I'm going to ask one more question on the topic of fuels right now, and then maybe we'll switch back to the socio-technical side of things. Since Stephen, you had just mentioned something about alternative fuels, and you mentioned green hydrogen in your video, and someone asked, how is green hydrogen produced, and how could it be scaled up to support larger portions of our energy systems?
Yeah, sure. That was a great question. I mean, the term green hydrogen really means taking renewable energy that comes from typically solar and wind, putting it into a process that takes water and turns it into hydrogen and oxygen. So you use electricity to change water back into hydrogen and oxygen. And then you take the hydrogen and you can use it for a variety of uses. You could put it into a fuel cell and produce electricity and heat. You could put it into a gas turbine and create electricity. You could use it in the making of steel or pig iron. You could use it and convert it into ammonia and use it for shipping. So really, green hydrogen in the end is the process of taking renewable electricity and converting it into hydrogen, where the starting point is water and the end point is hydrogen.
Thank you. All right, I'm going to take one more question and then we're going to pause for a little activity. But Amanda, we have a couple of questions here about that are coming from our video on socio-technical energy systems. So this question is, Amanda suggested that we should think of energy systems first in terms of the services that they provide, and then in terms of the fuel sources or primary and secondary energies. In doing so, she suggested that these two important concerns are separate, but are they? In other words, is part of the energy service what we want actually the energy system? In other words, do energy services such as food require particular energy pathways, such as local agricultural, in order to be most meaningful or fulfilling? And if the person who asked this question is here and you want to clarify, feel free to jump in for Amanda to help her out answering.
Just leaving a pause there in case somebody wants to identify him or herself. Wow, that's an interesting question, right? And I think that I welcome Elizabeth and Stephen. I welcome your riffing on this as well. You know, this goes on the premise that what we actually are interested in are functions in our lives, right? Rather than how we get those functions, right? So, you know, I'm very interested today in the function of warmth, right? For comfort. And if that warmth comes from a renewable source, you know, I'm happier. I don't mind if it. What I mostly want is the warmth, right? And so I'm very happy to switch from a fossil fuel source to a renewable fuel source if I can still be just as comfortable, right? It's really interesting when you talk about food in this context, right, and how we think about food systems, because in some ways, you know, the whole farm to table movement, right, is one example of how our interests in the nature of a product is starting to become, you know, in this country anyways, more and more attached to how that product is produced, right? And so the premise of really caring first about the energy services, right, is, you know, based on you know, I want to flip the switch and get the light, and whatever happens in the back end, I don't have time to worry about. But the more that we start to incorporate that worry about or that concern about sourcing, right, into our decisions, the more your point, you know, holds some sway, right? That we care about sort of the system that it implicates down the line. And I think that's part of the premise of our approaches here to energy education, is that we want people to care more about, you know, about what's going on down the line when you flip that switch, right? So that you may make a different decision. Elizabeth, Stephen, do you have perhaps more pithy responses to this question, or this prompt anyway?
I don't have a more pithy one, Amanda, but I think it's a great question, and here's how I would think about it. In the end, what we really do care about are goods and services as humans. And as you know, and then hopefully the next thing we care about is how do we get those things? So we should never start the question about how do I make uh, make kilowatt hours, or how do I make something really cold. You start with a question of what you want. And so if the goal is to have a hot shower, there's multiple ways to make hot showers. You can heat up water with electricity, you can heat up with gas, you can heat up with biogas, you can heat up with sunlight, and asking the question of, well, what do I really want? And then to layer on top of that, the question of, well, what matters most to me about how it's produced? CO2 footprint, on demand, infinite amounts. You have to ask those questions. And so when we turn energy on its head and think about it as a service or a product, such as a head of broccoli, that's what we really want. We want to eat this head of broccoli. And then we ask the next question, well, how many ways are there to produce it? And there are literally everything from we can conjure it up in a petri dish these days to we can ship it in from Peru in the middle of the winter. And if we ask that question, and then what matters to us, CO2 footprint, cost, whatever, then we can explore the options of how to get that goods or service and what it might mean to forego it for a period of time. For example, you're better off trying to take a hot shower in the middle of the day if you're using solar hot water, because that's when the sun's out, but you can store it at some cost and then take a shower at night or in the morning. So it's a very central question that I think we've missed a lot in the world, in the U.S. in particular, to start out by saying, well, what do we really want? And then what are the options to get there, and what are the impacts of those options?
Thanks, Stephen. I think we might have a follow-up question from Dominic. Please go ahead.
Yeah, thank you so much. Those are very important answers, thoughts. I just wanted to comment. So I was asking the question, and thank you for bearing with the complicated language, but it's something that I'm very curious about. And increasingly, I'm questioning whether it makes sense to use this energy services paradigm to think about what the actual end goal of energy is. And there are some other really good papers in this area that are focused on the capabilities approach and energy justice, how we might frame energy justice in terms of capabilities. And there's a figure, I don't know if I can share my screen quickly, but I guess this is in a paper that I'm writing that shows this quite nicely. So I think, and this is up for contention, but this is sort of an argument, right? That in fact, like eating a broccoli or warmth is actually a secondary capability, and what you really want is something more meaningful. And to me, that ends up framing the whole conversation about energy systems in a slightly different way. And to me, it points towards trying to develop energy systems that themselves provide meaning and that aren't just focused on some sort of secondary capability or something like you think about it in terms of Maslow's hierarchy of needs as well, like something lower down on that hierarchy of needs. So.
All right, thanks for that. Okay, so we had a little activity, but I'm going to hold off on it for a minute because we have quite a few questions still that I want to get to. So I want to make sure that we're answering your questions. So going back into our questions here. So we had, let's see. Oh, so we had another question that was about Sankey diagrams and the Sankey diagrams that are available that I wanted to get back to really quickly. And I think maybe if folks head over to the website, they might be able to find this there, but are there any diagrams that show how our sources of fuel and our uses have evolved over time? Or is that something that folks would kind of have to extract by looking at past Sankey diagrams and looking at the more current Sankey diagrams?
That data is available from the IEA and the EIA. The energy EIA is the U.S. version of the International Energy Association. And so that historic information is available. I think going back now, maybe to the early 19th century, were mostly wood, and then we evolved to coal, and then to oil and nuclear, et cetera. Not as a Sankey diagram, but as a total use or total consumption diagram.
Right, and we can send a couple of examples of those charts to the group, because there's great trend graphs, again, on the on the source side and on the usage side, not necessarily always with the connections in the middle, so not a flow chart so much, but certainly the trends are very interesting. And one of the things that you see when you look at the trends of the kinds of the sources of energy that we use, for example, in this country over time, is that yes, we are transitioning from, say, wood to petroleum to natural gas to renewables. But as we make those transitions of sources, they're actually typically additive, right? So we're not completely phasing out a prior source. We're adding on top of that source as our demand for energy goes up. And so as my old professor used to say, the Stone Age didn't end because we ran out of rocks, right? It ended because something else came into the fore and sort of built on top of that, but we still have this, embedded reliance on a prior energy source. So we'll get a couple of examples of those diagrams up to the group. Megan, you also might want to note that there are a few questions in the chat that have come through. One asking, so Memory is asking a couple of questions. One about where does lithium come from? And Stephen, I don't know if you have a quick answer to the question of the major sources of lithium on this planet, but you're quite right that some of these precious metals or minerals or rare earths are strongly located in specific regions of the world and not evenly distributed, right? And so a lot of our rare earths and minerals are located in China, some in some parts of Africa. I'm not remembering exactly where lithium is most commonly mined. Stephen?
Amanda,
Yeah,
I
no,
put up a
I
link
think we have
that
to,
showed some reports there of
Oh, great.
where it was
Thank you,
there, and
Elizabeth.
those charts are up there. And I think that piece of where we're mining it today is really interesting, because geopolitically, one of the reasons we don't mine in the US is because of our stronger environmental regulations. And so in some ways, it's easiest to produce those resources in other parts of the world. And so when we've tried to put in mining projects in the US, it's always very contentious and problematic. But there are, again, from national security considerations, efforts to try and make domestic production of these minerals as well. I think we could also think about it from a global equity perspective. Is it fair to finance our energy transition on getting, critical minerals from the poorest parts of the world, and have them bear the economic burden of our energy transition? So having other people bear the burden of our energy transition. So I just think that there's some very interesting and juicy questions here.
but I would also build on that, and it's a very topical question right now in Chile, where they're rewriting the Constitution and trying to decide how to distribute the wealth that might come from a vast, vast amount of lithium, and do it in a way that acknowledges indigenous rights, environmental impact, etc. And so the people of Chile could say, well, we're not going to mine our lithium. That's their decision, I guess. A different question might be, how do they do it in a way that is fair and, I guess, extracts the most value for their people? The other thing I would say is that this is the mining industry. There's a vast innovation available in the world of lithium. So, for example, there are startup companies right now that are looking at ion exchange methodologies to capture lithium from really, really large brine pools underneath the Mojave Desert, or in Southern California, in big lithium brine pools in Alberta, similarly. So I think what we should really do is think about, how do we get what we need at the lowest impact, and then how do we do it most equitably? And so it's not a black and white thing. It's not like lithium extraction is bad or bad for the people who own it. It's the question of who gets the rent, the money from it, the value, and how do you do it in a way, and what does it cost to do it in a way that's environmentally sustainable? And this is part of a much larger question I think Elizabeth has put on the table, which is we're trying to change our energy systems, but we have to build out an enormous amount of equipment and capital to do it. And where those things come from, who benefits from it, and who pays the price has yet to be determined.
Thank you, Stephen. Okay, so we have a few more questions here. And again, feel free to put new questions in the chat or raise your hand if anything comes to mind. So when we looked at the Sankey diagram, we saw that there's a lot of rejected energy that gets wasted. And someone asked, what process wastes the most energy globally? Is there something that we can point to, like lighting or aviation or something like that? Seems like maybe it's not just one thing.
Sankey diagram, what you see is, for example, in transportation, enormous amount of heat is rejected. The typical efficiency from a gallon of gasoline in your car to actually getting you to move where you want is about 15%. That's pretty bad. Historically, though changing rapidly, we would heat our homes with boilers that were 80% efficient. And electricity production has until recently been sort of pegged at about a 30% conversion efficiency. So most, but not all, coal-fired plants are 33, 35% efficient. Combined cycle gas turbine can get up to 55%. So I would sort of say electricity is really a problem, changing, and I would say transportation is a really big problem.
Great. Amanda or Elizabeth, did you have anything to add to that before we move on?
Sorry, I got kicked off with my bad internet. I don't know what
No
we're
problem.
talking about.
No problem.
Welcome to my life.
Yes. So I guess what I would say on that question about, efficiency is I appreciate that Stephen pointed to, the electricity sector and the transportation sector as places where there's big improvements to be made on improving efficiency. I think that, and I think that's helpful, but I think it's also, there are specific fuel sources, there are specific technologies that are deployed in different sectors. And so, it's also, I think, helpful to recognize that, when we're making a choice about what are we going to install, right? Or what are we going to plan for in our, our next local development? We can also make a really informed choice about those technologies. It happens, what I'm trying to say is it happens on a case-by-case basis as well as on that global basis. And so, yes, we need to improve the efficiency of the electricity sector and the transportation sector, but we also need, when we are confronted with a particular set of energy choices, we need to push hard for where can we stretch the envelope in getting greater efficiency. When we were making some decisions with the new building, the new Irving building on campus, right, we really wanted to push in the cafe, right, to have equipment that was as efficient as possible. Well, the food services industry isn't exactly prioritizing efficiency in its equipment. That doesn't mean that you can't still push for that, right, and find equipment that is better than the standard, right? If you're willing and able to put some resources up front for that. And so I think it's also about making those choices, right, to push for greater efficiency in all of our individual decisions.
Well, and can I just add to that? Because what I've appreciated, and Stephen, you'll always talk about how much more efficient our new building is going to be, the one behind Megan, you can move your head, Megan, than any other building on campus. But this shouldn't be an outlier. This should be standard operating procedure going forward, right? We shouldn't just have one special building for the Energy Institute. We should have every facility on Dartmouth become more efficient because we can. And that's the hard piece. That's the hard piece, is all of these small decisions that are made at so many different levels with people with competing priorities. And it's that institutional shift of making this energy and society story part of how we make decisions. That I think is one of the really big institutional challenges. And I know Stephen, you can't tell, but when he started at the Irving Institute, his head was a little bit rounder, but he's been pounding really hard to try and make Dartmouth more efficient over his years here. And it's a challenge because it's not part of our current way that we think about the world. And so when you go into your jobs, you'll be making energy decisions all the time, whether it's what paper to source, what copy machine to buy, what cars to ensure are part of your fleet. There's all kinds of decisions that you'll be making in your professional lives when you leave here.
All right, thank you. Okay, so we still have a couple of more questions, I think, here that we haven't quite gotten to. One of them is focused on transportation that I think we'll hold off on a minute because we addressed this question a little bit and we're going to be talking about transportation next week. But so we have another question here about our sociotechnical energy systems that I think is a little similar to a question that was asked last week. So I am going to pose it, and it's addressed towards Amanda and talking about something that you said in the video about the best approach to considering the socio-technical dimensions of energy systems is to ask questions. Yes, but what are the incentives to asking more questions about crypto energy systems or our hidden energy systems? So are there incentives to think about for energy systems to, I guess, raise questions and be less hidden? And I don't know if the person who asked this question wants to clarify that a little bit, but it sounds a little similar to a question that was asked last week about our energy system sort of being more visible, I think, to us. But yeah, if anyone would like to clarify that question for us, that would be great.
I mean, I don't want to take up too much time with my pesky questions because I mean, I guess maybe you get the theme of the sorts of questions I'm interested in, but yeah, I think it's an open question to me when you're thinking about the costs and benefits of various energy systems, whether it's possible to develop systems that incentivize asking the sorts of questions that we can convene here. It struck me last week, and it is very apparent in conversations with people about energy systems that there's sort of this, like, you're surprised that energy actually plays this huge role in your life. The question is, like, as we think about an energy transition, can we change that, or should we be thinking about changing that?
I guess I have a
I think,
response,
Dominic,
but
once you
Dominic,
start looking,
oh, go ahead.
I was going to say, I think, Dominic, once you start looking, you start seeing. Right? I mean, it's like that whole Plato's allegory of the den. Once you kind of think about the world not as just shadows, but as something else, it's hard to unsee it. And the challenge, I think, is that we don't have this conversation until we're at university. Like, why aren't we having this conversation in second grade when we're teaching about climate change? I mean, instead of the AP in just environmental studies, should we also have an AP in energy, or should energy be part of how we learn about our critical infrastructures in the world? Stephen, what were your thoughts on this?
Well, I guess I would, this is a bit of a broken record, but if you start with end use efficiency against the service or product you want as the opening question, and how do we do that, and what's the headroom to get better, you're going to find out there's huge amounts of opportunity. Roughly 90% of the energy in the world goes to waste. Sankey diagram not aside, there's huge efficiencies. And I actually worked to sort of build on Elizabeth's question about when and how do we entertain these things. I worked with a person who was part of the Milwaukee, his child was in the Milwaukee school system, and he's an energy efficiency guy at Johnson Controls. And they introduced, at least at one primary school, the notion that children would show up, whatever they were, fourth grade or third grade or something, how much energy does your family use? And then to start to compare, well, how much does your energy your family use versus this other family, all anonymized, obviously. And then what drives the energy efficiency? And this went from, whatever, let's just say a 6 or a 7-year-old, just some numbers, then some basic math, then a bit of algebra, So by the time you got to middle school, the children could actually differentiate between energy intensity per unit of service, basically, the total amount of energy, energy per family, and where it was going. And it's really interesting to me to think that we've been fighting this crazy issue around energy forever, and unlike cigarettes and then seat belts and other things, we haven't educated young people to say, oh, this is a difference. They can understand it. And then I think what was really interesting about that program I taught this guy about, and this is like 15 years ago, was that when the kids come home and ask about the energy bill, which the parents have never looked at, they've only paid for it, and they start doing comparisons, all of a sudden, the parents get really interested in that particular issue and that math problem and why are we using it and all that. So I think there's this revolution that could happen to have a whole bunch of, somewhat painful to deal with 12-year-olds nattering at their parents' ear about why is our number so high? How come we're using this much energy? And I think that would be a revolution in the U.S. and the world.
In the US, we did it with recycling, right? I mean, when a lot of us grew up, recycling wasn't a big thing, or it used to be, and then it wasn't. And now then it became, again, this kind of normalization. And once you get the 10-year-olds on the case, you start
You're in
seeing
trouble.
societal change.
All right, great. I think we have time for one more quick question. And we have another one here focused on fuel that's about hydrogen fuel cells. So are hydrogen fuel cells a better or more efficient energy alternative than solar, wind, geothermal, things like that?
Well, that's a big question to finish up on. I would say the answer depends, but let's just first talk about what a hydrogen fuel cell really is, and that's the fuel hydrogen, wherever you get it from, going through a device that actually produces electricity and heat at the same time. And so that's very beneficial. So if you had a really cheap source of hydrogen and it came into your house right now in New England, and you could produce the electricity that you needed for your home, and it produced a fraction of the heating need you had, you'd be pretty happy, assuming the fuel was cheap and the hydrogen fuel cell was cheap. And so really the holy grail of a fuel cell is that, one, to buy one and utilize it is cheap, and that the fuel coming in is cheap. And so I mean, this is me speaking personally, I imagine a world in the future, probably within the lifetimes of many people on this Zoom call today, where hydrogen can be produced, green hydrogen can be produced very cheaply from wind and solar. It can actually be stored relatively cheaply and delivered to the point source need, which might be your home, your business, whatever. And there are people, such as in the Toyota Motor Company, who think that hydrogen could play a role in transportation, where hydrogen would then go into fuel cells and be used to create electricity that would drive an electric motor. And so, I think right now we should think of fuel cells as a very, very immature industry at one level, although it's been around since, the Apollo era, and say, well, if we brought it to scale, what cost reductions would you see? In automotive today, because of Hyundai, Toyota, and a few other companies, they've driven down the cost of fuel cells about 75% over the last 10 years. They're still expensive. Another 75% may well be possible. So what I would suggest is we think about fuel cells as a really, really interesting option if we can get the costs right and we can get the input energy, which needs to come from green hydrogen, inexpensive.
All right, thanks, Stephen. So we are just about at time. Amanda, Elizabeth, or Stephen, any final words about our topics today that you want to share before we close out?
I just wanted to thank
Right.
everyone for showing up. This is great to see everybody, and it's nice to be able to have this conversation. Thank you. We wish we were in person, but thank you very much. I stuck a link into the DOE's Alternative Fuels Data Center that has a lot of different drivetrains too. So for next week, that might be a useful source to share with everybody as you're thinking about transportation sector change.
Great. All right. Thank you so much to everyone for joining us, and thank you for asking your questions. And hopefully you'll have more questions for us next week. And feel free to reach out to us with any questions. You'll be getting more communications for us about what's coming up next week, but enjoy the rest of your evening. And thank you so much for being here.
Thanks.
Bye.